Assalamualaikum everyone. My name is Muhammad Azri bin Ahmad, and today I will be presenting our project on the design improvement and analysis of an aircraft engine bracket. This work was conducted as part of the MMK 21103 Computer Aided Engineering course. Let's start with an introduction. The original bracket for the aircraft engine was made from titanium alloy T16A14V. This bracket had a total mass of 2.05 kg with a maximum displacement of 0.43 mm and the factor of safety which is 1.1. It's important to note that titanium production is highly energy intensive, which is more than 15 times that of steel. So our project aims to contribute to Sustainable Development Goal 12, which focuses on responsible consumption and production. We seek to redesign and optimize the structural engine bracket used in aircraft to reduce material waste and enhance resource efficiency. For the analysis, we use two primary software tools, which is SolidWorks for creating the new design and Ansys for checking the design requirements. The parameters we focused on were the mass, total deformation, and the factor of safety. So this is the rough sketch that I need to follow and create the new design. After several attempts, this is the final design which is sketched by me and I created it in SolidWorks. For the analysis, the new bracket design that I made before is going to solve by using Ansys. The material that I assigned is aluminum 7475. I chose this material because it is more like than the original material, which is titanium alloy. Here is the result for maximum total deformation, which is 0.34778 mm. This result uh, was lower than the original deformation, which is 0.43 mm. Here is the result for equivalent von Mises stress, which is 239.24 MPa. For this result, the stress is not required for me to analyze it, but I expect that the stress is not high from this value like 300 MPa and so on. As for the factor of safety, this new design also achieve a higher factor of safety, which is increasing from 1.1 from the original to 2.1 by ensuring even stress distribution and incorporating reinforcements in critical areas. This made the bracket capable of withstanding higher loads with greater safety margins. So here is the mass of the bracket is 0.77406 kg. The switch to 7475 aluminum combined with geometrical optimization achieved the lowest mass for the bracket and reducing it from 2.05 kg from the original bracket to 0.77 kg. This significant reduction was possible due to aluminum's low density compared to titanium alloy, along with an optimized geometry that minimizes excess material and utilizes structural efficiencies. Here I present the result for linear static analysis for the redesigned bracket. I chose aluminum 7475 for the new design. Using SolidWorks, I were able to create a bracket that met the requirements needs. For the final design result, it a mass of 0.77406 kg, maximum displacement is 0.34778 mm, and an improved factor of safety is 2.1736. So this result is more improved than the original one, which is the total mass is 2.05 kg, maximum displacement is 0.43 mm, and for the factor of safety, which is 1.1. Next, this is the result for thermal stress analysis. Without considering thermal effects, the von Mises stress was 239.34 MPa, maximum deformation was 0.34778 mm, and the factor of safety was 2.1736. However, when the thermal effects were included, the von Mises stress is increased to 961.45 MPa, deformation to 0.50022 mm, and the factor of safety dropped to 0.75204. This highlights the importance of considering thermal factors in the design. Consequently, the bracket operates at stress level where yielding or permanent deformation becomes likely and posing a heightened risk of failure. This situation underscores the necessity of accurately accounting for thermal effects in engineering design to ensure structural reliability. Here is the results for free vibration analysis. The objective of this analysis is to determine the natural frequencies and the corresponding the deformation of the bracket when subjected to vibrational forces. The first mode shows a relatively high frequency at 2486 Hz, indicating that the bracket is quite stiff. The total deformation is 101.43 mm, which is significant but expected for the first mode, as it usually involves the entire structure vibrating in a uniform manner. In the second mode, the natural frequency increased to 3205.6 Hz, and the total deformation increased to 57.986 mm. This reduction in deformation suggests that the structure is becoming more stable with higher modes. For the third mode, the natural frequency rises to 4985.1 Hz with a deformation of 63.656 mm. Although there is a slight increase in deformation compared to the second mode, it remains within a manageable range. In the fourth mode, the natural frequency is 6,364.1 Hz, but the total deformation jumps to 168.13 mm. This significant deformation suggests a mode shape that could involve complex bending or twisting of the bracket. And the phase mode shows an even higher natural frequency of 8,419 and 8 Hz with a deformation of 84.947 mm. The reduction in deformation compared to the first mode indicates a different vibration pattern, potentially involving less overall movement of the structure. Finally, the sixth mode has the highest natural frequency at 9730.6 Hz with a total deformation of 127.97 mm. This mode is high frequency and considerable deformation could be indicative of localized vibrations within specific areas of the bracket. For the discussion, the redesign of the aircraft engine bracket from titanium alloy to aluminum 7475 has resulted in significant weight reduction and improved performance in terms of displacement and factor of safety. The thermal stress analysis indicates that thermal effects significantly impact the stress and deformation, highlighting the importance of considering thermal factors in the design. In conclusion, the redesigned aircraft engine bracket using aluminum 7475 successfully meets the goals of reduced weight, improved safety, and enhanced sustainability. This project not only contributes to the efficiency and performance of the aircraft, but also aligns with broader environmental and sustainability objectives. So that's all from me for this project. Thank you.